Hello, dear colleagues, and today we're starting with our grand topic about artificial intelligence, and we'll talk how medical decision support systems are working if they are based on artificial intelligence solutions. And we already discussed how to distinguish the subfield of machine learning from other areas of artificial intelligence and computer science in general. We describe the model of fitting procedure in supervised learning settings and how to learn to separate supervised learnings from unsupervised learning in healthcare applications, how to understand the difference between structured and unstructured data, as well as some of the commonly used methods for representing unstructured data. And now we're familiar with common machine learning approaches such as regression, support vector machines, and decision trees, and how they can be applied to solve clinical problems. And of course, our current lecture is about these topics in depth, so we will talk about these topics deeper. And as something to begin with, let's dive into definitions of machine learning. We have formal definition, a family of statistical and mathematical modeling techniques that use various approaches to automatically learn and improve the prediction of a target without explicit programming code. And another informal definition is systems that improve their performance on a given task by interacting with experience or data. And inside machine learning, we can divide, according to various criteria, three basic paradigms. They are supervised learning, this task-based learning paradigm, for example, predict a value based on known facts. Unsupervised learning, data-driven learning paradigm. A classic example is clustering, when we're dividing some issues, some cases in different categories. And the third one is reinforcement learning, the most difficult paradigm, and it's based on learning from mistakes. At first, let's look at how computer programming works in general. The work of any program comes down to three components: incoming data, input data, processing of this data, and output data. For example, let's see I have a program that solves some kind of equation and it provides calculation of the area of a circle. The input data for it will be radius value. Processing will be raising the input value to the second power and multiplying by p, and output is our area of a circle value. Another major concern is detection of anomalies. The input could be, for example, ECG, and the output could be a medical diagnosis, such as CT segment evaluation, myocardial infarction, which will indicate infarction. In both of these examples, there is something between the output and that process which will work with input data to produce output information. In example 1, there is a mathematical construction, a formula, and in second example, there is a visual analysis of the ECG leads, which will lead us to conclusion, and the process we're talking about is what comes between input and output. And it's this process is being called a function. In traditional approach for computer programming, we intentionally write rules to process data input, and we will implement the translation algorithm using programming language, which will work with this input and produce our output data. And traditional computing is also called the rule-based approach. In other words, computer programs write functions with certain rules. A written program is a function or processing that computer could understand and use for its work. Now let's look at the fundamentally different approach, and this approach is called training. First, let's define the concept of supervised learning. A program written using this approach searches for, or in other words, learns or finds data uh, as a function that can accurately map our inputs to outputs. We then use this function to process new inputs and produce new outputs. If the cardiologist has already looked at the ECG and it is our input and recorded a diagnosis, which is output, then we are likely to have two sides of this equation. All we need to do is figure out how this function, which produces this output from the input, will work. Tutored or supervised training or learning algorithms is the process by which a program takes input-output pairs and learn the function that links them together. Note that we call this supervised learning because we provide input and output pairs. So we are in control of the model by giving the correct answers. Model as an object that undergoes training with a cheat teacher in this case. It represents or models the relationship between input and output. Learning this relationship means learning the function, which in this case mean setting up a set of numbers known as parameters. The model is completely defined by its parameters and the operations between them. The model is sometimes called a function approximation. It approximates a function between input and output. Once a program learns a function that works well, we can use it instead of software that would have been written by traditional computer programming. We can take new inputs, apply them through the learning function, and produce new outputs. This is the ultimate goal of supervised learning. It's important to understand that when learning with a teacher, programs still need to be written exactly like that, just like traditional computer programming. Where integrate this program is completely different approach. It consists of searching or studying the exact mapping function without first specifying it. Let's take a look at basic terminology. Example, it's input-output pair. Sign or feature or characteristic is a part of example that's entered into the model. Label, it's a conclusion, the part of the example that is compared to the model's prediction. It's our output or result. Dataset, it's an example of sets It's a group of examples. Prediction, the result of a model that has learned from many examples of inputs and outputs and can now accept new inputs and produce new outputs. On the side of dataset terminology, we have educational set or training set, a set of data that is given to the model to learn a function that relates input to output. Test set or validation set, a non-training dataset used to evaluate or test the generalized performance of our model as we develop it. Also, it's used to select designs uh, for our relationships and hyperparameters and other aspects of a program training during the training process for the model. And we have test dataset or test set which use the same approach as validation datasets. It's not being used for training, and it's being used when testing the effectiveness of a model generalization on examples that are not fully visible during any aspect of model development. Let's take a look at learning cycle. It's an iterative process of training that gives the model multiple chances to learn highly generalized features from the training set. It have certain stages in its structure. We'll start with the launch of the program. The program customizes the learning environment with chosen hyperparameters and initialize the model with a random function. Introduction the model to examples from the training set in order to study the function from inputs to outputs. Evaluation is how the function works on the test set. If the model performs better than ever before, we keep that version of the model. Repetition of the steps 2 and 3 until performance on the validation set stops increasing. And we usually repeat this cycle for different settings of hyperparameters. This process is called setting hyperparameters. Different hyperparameters give different models characteristics. Once we're satisfied with the model performance on the validation set, we can run this final model on test set. We can use different types of data. We can use structured data. It could be patient laboratory values, diagnostic codes, and so on. They are commonly used with more traditional statistical models. Structured data is typically entered into a model as a list or vector of numbers. Unstructured data could be images or natural language, for example, text reports. Images are usually represented as a number grid where each number represents a density at a given pixel location. In grayscale images, there is only one grid. In color images, three grids are combined on each other: red, green, and blue grids. This information could be represented by so-called word representations, and it's usually used for text processing. Word representations are geometric numeric vector representation of words. Supervised learning solves two main classes of problems: regression and classification. Regression is a forecast based on samples of objects with various characteristics. The output should be a real number. If the model outputs real numeric values, then it solves regression problem. If the model predicts a category or class, it describes classification problem, decides on classification problem. The classification problem has a finite number of answers or categories. Labels are numeric categories, identifiers. In this case, the labels are simply numbers that act as category identifiers. Mathematically, the objective of learning is to minimize the difference between the outputs generated by the model function and the true label for each sample in the training set. Loss called the difference between the output of the model function and the true label. We typically average or sum the losses for each data point we have. If the model is poorly trained, there will be large losses. If the model is well trained, then the difference between the true label and our feature will be small on average, and hence the resulting loss will be small. Uh, the model updates its function on match the input data to match the input data to the labels as accurately as possible. It's called just adjustment of the models, and the model updates the function by changing its parameters. Parameters are numeric values that are used to perform operations on input data. Let's take a look on regression models. Let's look at a simple example. It has long been known that there are many wild monkeys in Brazil, and the warmer it is, the more often they jump from branches. For many years, uh, Brazil recorded data on the number of monkeys jumping from branches and air temperature. As birthday presents, and we can use this data. You want to explore this relationship, and first thing you do is plot this data. As expected, we see a clear relationship between air temperature and monkey jumping from branches. To make sure that the relationship is practically linear, we can draw a straight line to approximate this relationship. Of course, this line doesn't connect every point to every point, but it does show that there is a connection between temperature and jumping, and we can write it down as you can see on this picture. If our function is expressed as a function of uh, known parameters, we can label them, and parameters by which the signs are multiplied are called weights. Parameters added to the product of weights and attributes are called biases. In some sources, you may find other designations, for example, scales, weights, or errors. Accordingly, in order to predict the number of jumps of wild monkeys, it will be enough for us to substitute the actual temperature value into the expression, which will show us the result. And the error parameter is a number added to the characteristics. Bias phenomenon is a concept related to model performance and algorithmic fairness of this equation. This phenomenon of observing results that are thematically misreported to the faulty assumptions. The second standard type of problem for supervised learning is called classification. In problems of this type, the input values can be sets of structured information or unstructured information, images or medical records. And the labels are a designation of what is present in these images. What is the difference between classification and regression? Classification labels are categorical. They strictly describe class members or lack of this required class. Moreover, if we're talking about a prediction, then in classification models, output will present probabilities. The model will predict in classification what is the probability that an object that which have certain characteristics belong to each category. The membership probability in this case is calculated, for example, using a function like sigmoids. For classification models built on the principle of logistic regression, this mathematical concept is often being used. One of the important definition related to classification problems is the probabilistic value. We use this value as a boundary between categories. By default, the decision boundary is set to 50% probability. Let's look at the example. We built a binary classifier that uses tumor size to classify into normal and abnormal. As we can see, depending on the location of the operating point, decision boundary, some cases may fall into different groups. To suit the question being asked, or depending on the use case of our model, we can shift one operating point. And so if we're making a screening test in healthcare in which false positive are acceptable but false negatives are not, the operating point can be adjusted so that more examples are classified as positive. In this case, setting decision boundaries for several characteristics is similar to setting one characteristic. Let's look at the classification setting. Uh, In both single feature and dual feature cases, we can visualize each label as a separate dimension, whose values separate the categories. The model still needs to learn a feature with a decision boundary that separates data points with different labels, so-called Y. However, in the case of two features, we need to adjust the parameter values corresponding to both features, x1 and x2, to find a suitable model. Recall that parameter is a parameter that values are model weights multiplier by features. Displaying the decision boundary is also similar. Recall that the overall decision boundary is where the function outputs is more than 0.5. Since there is a 50% chance that the output for a sample location on the decision boundary will be 1 versus 0. Since the presence of pneumonia in this case is a binary classifier that that's we can only have values 0 and 1. We can flatten this entire figure to two dimensions and mark the y only with color. In other words, the point whose y is equal to 1 is red, and the point where y is 0 is blue. We can also indicate the decision boundary by drawing a line wherever our function takes on a value of 0.5. In essence, setting a decision boundary for two features is a direct extension of setting a decision boundary for a single feature. Also, it's harder to visualize the same idea, which could be applied to any number or signs. For binary classification, the geometric visualization is similar. We need to find the function whose decision boundary lies between two sets of samples. We have already mentioned in this course works of human nature as well as a modern correlation to these works, the theorems called no free lunch theorem or the no free NFLT theorem. On single machine learning algorithm is it's suitable for all problems. When applied to supervised machine learning, the meaning of this theorem boils down to the fact that there is no algorithm that works better than other on the entire set of problems. If a certain algorithm works better, faster, more accurate on some tasks, it means that it will be worse on other tasks. The theorem is of fundamental importance. Of course, there are specific problems that can be solved by specific algorithms selected for these tasks, but it's impossible to generalize the selection method. Polynomial regression is useful for processing non-linearly separable data when the best fit will be a line and this line couldn't be a straight line. So regression will fit a curve, not a line, but a curve. There are different other types of regularization and regression algorithms which could uh, provide additional diversification of linear regressions for specific tasks. It forces the learning algorithm to not only feed the data, but also to keep the model weights as small as possible. Lasso regression, last absolute shrinkage and selection operator, least absolute compression and selection operator, so-called regression, is another regularized linear regression version, which is a elastic model with regularized size of the weights. At their core, all these types of regression are functions that can act as a classifier and can be turned to better match the relationships between features to predict the correct label. Next algorithm is decision tree. It's also called the basic of classification tree or regression tree. These decision support methodologies used in machine learning, data analysis, or statistics. They are a decision-making algorithm fixed in the form of a tree in a digital form. A direct connection graph with there is no cycles in there and branch nodes which will provide yes and no types of decisions. And going through these branches and different nodes in them, we're able to find the values of the features and values for the objective function in general. The purpose of creating a tree is to implement a model that would predict the value of the target variable, and based on this uh, value will have answer formalization in research question based on the input data. Trees can be used for both classification and regression. When using decision trees for classification problems, the leaves will contain the class values. When using a tree for regression, the prediction outcomes can be considered as a real number. For example, length of hospitalization. Advantages of this algorithm are that it can be trained very quickly using high-dimensional datasets. Construction doesn't require special data preparation, normalization, adding dummy variables, moving missing data, and so on. The algorithm is easy to understand and interpret. Each branch in the tree is a decision point based on some relationship between features. It works well with both discrete and continuous variables. Disadvantages of these algorithm are that problems uh, to obtain the optimal algorithm. The problem of overfitting that occurs when building a structure that is too complex. Sometimes the result may not be accurate. This effect can be mitigated by using variants of decision trees such as random forests. Algorithm based on Begging, Brainman, and Cutter. The main idea is to use a large ensemble of decision trees, each of which by itself gives a very low classification quality, but due to their large number, the results are very awkward. At the time of publication, the results were the best in the class. Random forests improve decision trees by combining all the predictions of many decision trees. Typically, decision trees are trained on all features using all samples in the training dataset. Each of the decision trees in the random forest algorithm sees only a subset of the parameters available for each sample. Only a subset of the sample in the training dataset will produce results. Advantages of these methods are the ability to efficiently process data with a large number of features and classes. And it's insensitive to scaling of feature values. It works equally well with both continuous and discrete features, and algorithms lend themselves well to parallelization in this process. Diversification of decision trees can lead to the construction of individual bad classifiers, where while other decision trees of the created set will be correct. As a result of reaching consensus, the trees can classify more correctly than any single decision tree. Of course, there are flaws in this algorithm. Learning is more difficult than decision trees, and these models will have bigger size. Support vector machine. It's a very popular supervised machine learning method, and it's used for classification and regression problems. This is a method from the family linear classification and also could be considered as a special case of Tikhonov regularization. Support vector machine is also known as classifier with maximum clearance. The main idea of the method is to construct a hyperline for a space of dimensions equal to number of parameters belonging to a space uh, of this hyperline is where it's a point for a two-dimensional space. It's a straight line. For the three-dimensional space, it's a plane, and so on. Separating the sample objects in the optimal way. So we'll have this hyperline in hyperdimension, which will be used in a similar way as linear classification in a two-dimension reality. The algorithm operates under the assumption that the greater the distance gap between the separating hyperline and the objects of the separable classes, the smaller the average classifier error will be. The method is intended for linearly separable samples, but it can be generalized to linearly inseparable ones. So, what are the benefits of this method? The problem is well studied and has a unique solution. The support vector machine is the equivalent of a two-layer neural network, where the number of neurons in the hidden layer is determined automatically as a number of support vectors. The principle of the optimal separating hyperline leads to maximization of the width of the separating strip, and therefore to a more confident classification. SVM is more robust to outliers. There are, of course, many problems with this algorithm. It's unstable when we have noise in our data. Outliers in the source data become reference offending objects and directly affecting the construction of the separating hyperline. General methods for constructing kernels and rectifying spaces that are most suitable for the specific task are not described in this method. There are no feature selection, so each parameter will be considered as important. It requires a manual selection of the right way for the width of this space between parameters. It happens that we have a very large data set. The data in this set isn't labeled in any way. Uh, that's it doesn't have any labels, and we have no way to label it at our discretion. In this case, a class of algorithms, so-called supervised, unsupervised learning, is used. Learning without a teacher, this class of solutions is aimed to studying a set of unlabeled examples and grouping them according to the same common features. Standard tasks here for unsupervised learning are clustering problem, so distribution of data into groups, dividing all clients of a mobile operator according to level of solvency, assigning space objects to the category or another, one category or another, planet, black hole, star, and so on. Dimensionality reduction problem, reduction of a large number of features to a smaller number, usually 2, 3, or 5, for the convenience of the subsequent visualization. For example, data compression. In unsupervised learning, the challenge is not to in obtaining the grouping, but in evaluating it or determining whether the grouping that is discovered actually makes sense. As applied to healthcare, the issue is whether the presence of a grouping option, so-called clustering, or the fact that a new patient is assigned to a particular group will trigger action in the form of offering different treatment options for different groups of or adopting a specific clinical decision for the patient. As we already covered, there are three main machine learning paradigms: supervised learning, unsupervised learning, and reinforcement learning. All these paradigms are fully reflected in deep learning. And if we consider the meaning of supervised and unsupervised learning, the reinforcement learning is left for now. And reinforcement learning currently is the most complex area of machine learning algorithms, and the application of this paradigm in healthcare is one of the least studied machine learning problems for the subject area. Reinforcement learning is based on the idea of a model interacting with the environment as an agent. Continuous observing the current state of the environment and making decisions based on it is an essential part of reinforcement learning. We use the word agent here because taking actions is a central concept in reinforcement learning. AI agent, this is an essence of our algorithm. This concept is often used in gaming or simulations on environment. The application of the paradigm in healthcare reveals two global problems. There is no clear methodology for environmental modeling. In games, simulating the environment is very easy because you can just run the game, and in healthcare the stakes on experimentation are much higher. There is no explicit method of enumerating the agent. Games have explicit scoring mechanism. In healthcare, it would be dangerous and naive to define a patient's health based on this criteria. However, in healthcare, this learning paradigm is applicable in situations where an application needs to constantly interact with the environment and adjust its actions based on the environmental feedback, such as to optimize treatment strategies in a robotic surgery, for example. For today, it's all. Thank you very much for attention.